All right, here we're looking at section 8.1, and our learning targets for the section are to use similarity statements. Then we're going to be finding corresponding lengths in similar polygons. Then we'll be looking at perimeters and areas in similar polygons. And then finally, we'll be given two figures, and we have to decide if they're similar or not. So let's get started. So the first thing we want to know is that corresponding parts of similar polygons share some information. So if I'm looking at these two polygons and I'm told they're similar, and this little symbol right here means similar, so I'm told here that ABC is similar to DEF. So I know then my angles are, my corresponding angles are congruent. So if I draw these out, right, such as this is, I see that angle A corresponds to angle D. If these triangles are similar, then the angles are the same. Then I know that the ratio of the side lengths is the same. So if I measure DE, right, so this length is going to be in a ratio with this length, and DF is in the same ratio as AC, and then my ratios all have to be the same. So what I really can think of is I take each side length of the smaller one and multiply it by the same thing. That's what this K is. It's just I multiply by the same thing to get the side lengths of the big ones. So I know my angles are the same and my side lengths are in a constant ratio, right? That's what my ratio is big. They're not the same length, but they're in a ratio. One thing I can look at too is when I'm writing it like this without drawing it out, I know some stuff, I know a couple things about these triangles. So the first thing I know is that I know that angle A is congruent to angle D, right? Those are my corresponding angles, and I know that because they're written that way as well. So when I'm writing about my triangles, I have to be careful what order I put my letters in. So that's just another way I can use this information to help me with similar figures. So now let's look at this example. So in the diagram, RST, triangle RST, is similar to triangle XYZ, right? So you see how they're written and drawn so that I can see my corresponding pieces. So first I want to find the scale factor to go from my RST to my XYZ, so I'm going to be going this direction. So what do I multiply this number by to get this number? And what do I multiply this by to get this number? So that's what we want to start with. So first I want to write my ratios out. So I'm going to look at XY, which is 12, and RS, its corresponding side length, which is 20, and then I can simplify that 3/5. And I just want to double check. So I take my YZ, which is 18, and its corresponding side, which is 30, 3/5. And I finally check my last side, my ZX, and my TR, and it's also 3/5. So my scale factor is 3/5. So that tells me I'd multiply the big one times 3/5 to get the little one. And I know that because all of my ratios are the same. So I know for sure also that we have similar triangles. So now for part B, I have to list all pairs of congruent angles. So I know that angles that are corresponding are congruent. So I know that angle R is congruent to angle X, and I know that T is congruent to Z, and S is congruent to Y. This is also why it's very helpful to draw your triangles, how they're written. So if I start with RST, right, I start at the bottom and I go across, I want to start that way with the X. So they're labeled the same and so they're in the right order. So now for part C, I'm supposed to write the ratios of the corresponding side lengths in a statement of proportionality. So here's all I have to do. Because the ratios are equal in part A, here's what I know. I know that XY over RS is equal to YZ over ST, which is equal to ZX over TR. So you'll see I have all of the side lengths of my small triangle on top and all of my big triangle on the bottom. It doesn't matter if the big triangle's on the top as long as they're all three the same. So I only have my XYZ in the top and my RST in the bottom using these same ratios that I wrote in part A. So this is just my statement of proportionality. Because I know they're equal, then I know that the side lengths are equal right there. Okay, so here is your first monitoring progress, kind of doing what we just did in that last example, so try it and see how you do. So now here's our another core concept. So if two polygons are similar, the ratio of any two corresponding lengths is equal to the scale factor of the similar polygons. So let's actually look at what that means. Okay, so in this diagram, and I'm told DEF is similar to MNP, I'm asked to find the value of X. So here I have a triangle with a missing side length. right? But I know that these two triangles are similar, so I can find that missing side length. So I know that they're proportional. So the first thing I want to do is write a proportion. So I'm going to take two of the sides that I do know. I know one side from each triangle that's corresponding, and write a proportion that. So I know MN, and I know ED, and those are my corresponding sides. And then I'm going to use the side that's missing as part of my proportion. So then I substitute what I know. I know the length of MN, and I know the length of ED, and then I also know the length of EF, right? So now I plug in what I know, and then I cross multiply, right? Because when I have two fractions, I want to get my x by itself, so I cross multiply, which ends up giving me 18x equals 450. Then to get x by itself, I go ahead and divide by 18, and so then I know my x value is going to be 25. So then I can rewrite this as the side length EF, or the value of x, is 25. So I used the information that I knew to write a ratio. So when we're dealing with similar triangles, you're going to be writing ratios over and over. That's really what we're doing here. So here's something pretty similar, right? So again, I have two triangles that are similar, and I'm supposed to find the altitude, PS, right? So I can leave the triangles drawn like this, or I can redraw them so they're labeled and they're standing in the same way. But let's just see. So first thing I have to do is find the scale factor, right? If I'm told my triangles are similar, I always want to find my scale factor first. So I know that TR, this length, and this length are my corresponding sides, so I want to find the scale factor between the two of them. So I've got TR over XZ, so I know that these are the numbers that I was given, so I know that my scale factor is 3/4. So I can use this to write my proportion, right? So I know that PS over PY, so my altitude over my altitude, is the same thing as my little triangle over my big triangle, right? Little triangle, big triangle, little triangle, big triangle. And it's really important when we're writing these proportions to keep the similar things together. So I can write my proportion, then I substitute what I know, and I'm told in my picture that PY is 20. So now I just have one missing thing, so I multiply, I cross multiply, right? So I can do 3 times 20 and PS times 4, or I can just multiply both sides by 20, and I end up finding that PS is 15. So the length of this side is 15. And the first thing I always have to do is kind of find my scale factor, and then I can find any missing length that I'm dealing with. So here are some more monitoring progress to see how you're doing with these ones. Again, we're finding some missing lengths based on what we know about our similar triangles. So the first thing you're going to want to do is to find your scale factor and then go from there. So now here's our first theorem for this chapter. So theorem 8.1 is perimeters of similar polygons. So if two polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding side lengths. So if I know the ratio of their individual side lengths, I know that that is also going to be the ratio of the entire perimeter of each of the polygons. So let's look at an example here. So a town plans to build a new swimming pool. An Olympic pool is rectangular with a length of 50 meters and a width of 25 meters. The new pool will be similar in shape to an Olympic pool, but will have a length of 40 meters. Find the perimeters of an Olympic pool and the new pool. Okay, so we're just dealing with perimeters here. So when you're taking notes here, don't write all this out. This is not information we need. We just have to think about it. So I want to think about what I need and what I know. So I know that I'm given the length and width of a rectangle, and I have to figure out using similar rectangles, and I'm finding the perimeter. So the first thing I want to do is I have to find the scale factor of my similar rectangles, and then I can use that to help me find my new perimeter. Okay, so my new pool is going to be similar. My scale factor is the ratio of the lengths. So here I was told an Olympic pool length is 50, but the pool that we're going to be using is 40, so I have to find the ratio of those two numbers, which is 4/5. So then I have to use this with the perimeter of what I know, right? And I cannot find the perimeter because I add 50, and the top is also 50, so that's 100, and I have a side of 25 and a side of 25, so that's 150 right here. So I have that. So now I can write my proportion to find the perimeter of my new pool. So I know that my original perimeter was 150, and here's my ratio, right, that I found from my side lengths, and I can use this to find my perimeter of my new pool. So once I write the ratio, I can solve for x and find the perimeter of my new pool. Okay, so now I can go back and double check. So I can plug in that 120 over 150, and it does equal 4/5, so it does simplify to that. So I know I was right in my math. So the perimeter of my new pool is 120. So this is a little bit easier, so I don't have to find each individual side length of my new pool and then add them all together to find my perimeter. I can actually just use my scale factor to find the new perimeter without having to find each individual length, which can actually save us some time. So try this one, this monitoring progress, and now we're just dealing, instead of with rectangles, we are just dealing with pentagons, but they are again similar. So use what we just did there to find some side lengths, and then you can find the perimeter from there. Okay, so now here's our second theorem. Now we're going to be dealing with areas of similar polygons. So if two polygons are similar, then the ratio of their areas is equal to the squares of the ratios of their corresponding sides lengths. The biggest thing here to remember is with perimeter, we're just looking in one direction, right? So I don't have to square anything. I can just use my scale factor. With area covers two dimensions, right? Area kind of goes up and down and left and right. So I have to use my squared here. So let's look at an example that'll help us make sense. So in my diagram, this triangle ABC is similar to DEF, and I'm asked to find the area of triangle DEF when I'm given a side length for each and the area of the larger one. So let's look at this. We first always want to find our ratio, so then I can write and solve my proportion to find my area. So I know that the area of the big one over the area of the little one is equal to the side length of the big one over the side length of the little one squared, right? And I know because I'm dealing with areas, I have to square this. So then I plug in what I know. I know the area of the big one was 36. The side length that I was given was 10 and 5. So then I can square that information. So I squared that. So when I'm squaring a fraction, it can be I square the top and then I square the bottom. I square the numerator, then I square the denominator. So that's where I get 100 divided by 25. So now I cross multiply since I have an equal sign and two fractions. So I end up with 36 times 25 equals 100A. Then I can simplify, and then I see I'm multiplying, so I go ahead and I divide and I solve for A. So the area of my triangle DEF is 9 square centimeters. So here is your monitoring progress for area. Try this. Area can be the very tricky part in this because we're looking at squaring some information, so we have to keep track of that. So now let's look at our last learning target. We're deciding whether these figures are similar, right? And then I have to explain. So the first thing I would do is I would make sure that they're drawn, right? Like I could follow it. So I start down here, A, B, C, D, E, and it goes clockwise. So I notice over here that my second figure, my red one, starts down at the bottom, but it goes counterclockwise. So I have to keep that in mind when I'm just looking at the figures. So I know if figures are similar, then their corresponding sides would have the same ratio, okay? So I have to look and see what I'm given. So I know that, let me find my marker, that this side length corresponds with this side length. This one corresponds with this one, right? And I can just kind of continue what I know corresponds with each other and see if I have a similar ratio, see if my ratio is the same in all of those. So I can say, look at each piece individually. So if I look at these red ones, we're going to look at the little one divided by the big one. So then I can look at the little one divided by the big one. And then we'll look at this one, the little one divided by the big one. And I needed this color, the little one, we're up top here, divided by 9. And then I've got my purple side, so then I have 4 divided by 6. So now if I look at all of these fractions, right, the little figure divided by the big one, if I was to simplify all of these fractions, they all end up with the same factor. So I know that since they're all the same, that yes, these figures are similar. Okay, so this also tells me, right? Remember back when we learned about transformations, we learned about a dilation, which makes things bigger or smaller. So I know that a dilation with center A and a scale factor of 2/3 moves my shapes. So here we're just showing it, but I know that these are actually not similar because my angles are different. Okay, so the only angles that I'm told are A and K. So even though my side lengths have that same ratio, my angles are not the same. So they're not similar figures. So both of those conditions have to be met in order to say that figures are similar. The ratio has to be the same and all the angle measurements have to be the same. So I know that these two pentagons are not similar. Even though I looked at all the ratios of the sides, I was not given enough information about the angle measurements to say that yes, they are similar. So keep that in mind when you're going through this. So now I want you to go ahead and try these and see what you think. So the red shape, remember, is when we're talking a regular hexagon. That means all of the side lengths and all of the angles are the same. So go ahead and try and see what you can come up with for these monitoring progress. So now let's look back at our learning targets and see if we met them. So using similarity statements, that's what this is kind of using. Which angles correspond, which side lengths correspond. Those are our similarity statements. Okay, so then we were able to use our similar figures to find missing lengths that we had. So then we looked at finding perimeters and areas. Remember, the areas are kind of tricky because I'm looking in 2 dimensions, so I have to square my ratio. So then I could look at 2 figures and deciding whether they're similar or not. And when we're deciding if figures are similar, we have to look at the side lengths and the angles. We can't look at just one of those 2 things. So now that we've met our learning targets for this section, go ahead and please work on your homework for 8.1.